Alright, so this whole gravity thing, it's driving me nuts. I saw another video today from the Wisecrack guys and talking about string theory and how they were trying to get string theory to be the theory of everything. And I'm like, I'm not a physicist, I'm not a quantum physicist, I'm not an anythingist, but what irritates me is that my theory for gravity is so simple, and it fixes so many problems. It answers a lot of the tough questions. But I think the reason people don't like it or don't hear it or don't want to understand it is because in order for my theory of gravity to work, the holographic reality has to be true. What I mean by that is that gravity is the ultimate evidence that we live in a holographic reality. And gravity is actually a consequence of space-time. And what I mean by that, like if you've seen, so scroll down and watch the videos. I put together a series of videos that I did on TikTok actually, and then kind of spliced them together and put them in here. So go check that out. But I want you to do a thought experiment. In fact, you know what? I want you to go do an actual experiment. I'll do an experiment with this later so I can kind of, show you what's going on. But if you look at the Einstein's model of gravity, where he takes he says that gravity is kind of like if you take a bed sheet, you put a bowling ball on it, and it makes that depression in it. And then if you were to roll a marble by it, then the marble would kind of follow that course, and then eventually it would want to go down and settle with that lower place in the bowling ball. And that's all well and good, except it's only two-dimensional, right? So it doesn't account for the fact that anything that has mass has gravity, right? And because that would also imply that, I'm walking around on a two-dimensional, because I have mass. I've got more mass than I wish I did, but I have mass, and that means I have gravitational force, which would imply that I'm walking around on a two-dimensional plane, and things are, coming towards me. But they're coming from the top. They're coming from everything's coming from three dimensions, which doesn't work, So the only thing that works is you'd have to have something that can pull in all three dimensions. It has to be like that. That's my pulling from three dimensions. But what that has to mean, though, is that, so where would that energy come from? So here's the experiment that I want you to do. And I'll do a video on this later today, because I'm sick of talking about this, because it's so obvious. Once you hear this, it's the most obvious thing in the world, and you won't believe that nobody's thought of this before, because I'm not that smart. But what I want you to do is take a sock, right? So take a sock. I got socks, right? And what I want you to do is take an object. I don't know, got a tape measure. You got a ball, something like that. Get it down in there. Put it inside the sock. Maybe an orange. If I would have planned this better, I probably would have gotten an apple, a bowling ball, or something like that. Right, and you get it all the way down in there. I'm going somewhere with this. Right? So now, I got a tape measure inside of a sock. These are my Wrangler socks. I love my Wrangler socks. And then what you do is you get another object. What have I got? What have I got that's kind of heavy? I don't know. How about a TARDIS? Take a TARDIS. No, you know what? Because it's timey-wimey and wibbly-wobbly, and gravity is tied into time and stuff like that, I'm gonna use Doctor Who. And a tape measure inside a sock. Okay, so it's the Tom Baker doctor, number 4. That's my doctor. And you stuff him inside the sock, right? And then, so he's in the sock. So is Doctor Who. And you take the sock and tie it in a knot, like this. Okay, So, Doctor Who, tape measure, okay? And then you take the sock. So you can do this without breaking something, right? And you throw it. Like that. See? You go like that. That's what gravity's doing. Okay, so, if you notice that when it pulls, when it spins, the heavier object is going to be more likely to stay in a central location, and the lighter object is going to be the one that kind of moves around it, right? But there's going to be like a point of rotation, which is going to be somewhere in here, so they're going to kind of move like that. And if you watch, the objects in the solar system, then that's what they're doing, right? So this is what the gravitational poles are doing to each other. But what's interesting, in fact, we know this so well. We know this so well that they use the same idea to be able to find stars that have planets moving around them, because they'll find a star that has like a little bit of a wobble to it. And based on that wobble that they find, not a wobble, but like a pulsation that it's moving back and forth a little bit, right? And they can tell how big the planet is that's going around it, because that's what it's doing, So Doctor Who is the planet, and the tape measure is the star, right? And the sock is gravity. So that's what it's doing, okay? Now, but what is this? What's the sock? The sock is actually space-time, right? So, and you have to picture space-time as being this infinite computer monitor, but a three-dimensional infinite computer monitor. How does that work? All right. So here's what's happening, okay? And again, go check out the TikTok video. Scroll down a little bit and check out the TikTok video because it's pretty interesting. So, all right. So let's go back. Let's go down to the quantum level real quick, okay? And think about something called the Planck Length, right? This is the most important concept in this, is the Planck Length. And the idea is that, and they've mathematically proven this, I'm not going to get into that, but the idea is that is the distance that light travels in a second. It's essentially the Planck length, okay? And there is, there's also a concept called quantum foam. And I want you to Google that and check it out. Because when I started to get this idea, I realized that, there had to be something like this Planck length had to be something that was like quantum foam. So I started researching it, and I found the concept of quantum foam. I forget the scientist's name, but it was like 1927 he came up with this idea. And, I thought he'd come up with this brilliant idea, but it turns out it was almost 100 years ago somebody knew about this kind of stuff. But the problem with the quantum foam, and the reason why it never really went anywhere, is because they assumed that it was like the bubbles in the sink that are just kind of like this amorphous blob of moving things all over the place. But in order for gravity to work, in order for my theory to work, then each bubble within that quantum foam has to have a positive and a negative charge. It has to be like a little magnet. It has to have a positive and negative poles on it, right? Which would imply that it's spinning. Can you get that? So imagine, if you will, magnets. You get like little steel ball magnets, right? And they got a positive and a negative. They got the separate poles on them, right? Now take those magnets and put them together in a block, right? Get like 5,000 magnets. They're like little steel ball magnets, and put them together in a cube, right? And that is effectively space-time, because they fit together in a grid, and they'll naturally find their own polarity so that they can, fit together like that, right? And they'll be and then you have this very, very tight grid, okay? Now, what happens though is that they're not solid, they're not magnets. You know, they are, I'm not going to get into what they are, but they are transductors, maybe. You know, they allow for light to pass through them. So maybe they're like a prism. You know, maybe they're like the crystalline. In fact, that's exactly what they are. Is it's a crystal structure, okay, but impossibly small crystal structure. And what happens is when light travels through them, okay, and you have to remember too that light is not a particle like you think it is. So when I say particle, you think of like a thing, you know, you think of like Doctor Who, you know, like you can touch it and feel it, and you know, it's a particle, like a particle of dust or a particle of sand or something like that, but it's not. Light is an energy packet. That's all it is. It's an energy packet. It's an energy potential, right? That's like radiating energy. In fact, I think it's at MIT where they develop a camera that can photograph. It can make a video of a single photon traveling because it films at the speed of light, and you can see this photon that's traveling through. They ran it through a bottle of water, and it does all this kind of crazy stuff. So it's not like a particle. As it's going through, it's like radiating energy out from it as it's moving because it's only energy. But what that photon does though is as it's traveling through that grid of magnets, the energy in it excites those little individual magnets and it pushes them apart a little bit, right? It puts a little bit of energy into them and it pulls it apart. And when you pull that apart, if you take two magnets and you pull them apart, what that does is it creates a negative energy space in there. And that negative energy space wants to be filled by something. It wants something else to come into it, right? So different atoms and particles and things like that have been developed based on light and kicked out of stars and also the kind of stuff, iron molecules and these sorts of things that have kind of collapsed in on each other, go into those spaces that are being pulled apart, and they get sucked into them and sucked into them and sucked into them and sucked into them and compacted into them, right? And the more things that get back compacted together, the more negative tension there is within the fabric of space-time, and it starts to pull itself apart a little bit more and a little bit more and a little bit more. And the more things that get pulled apart, the more it wants to pull things into it, right? So, and that's why anything that has mass has gravity. Because the more mass something has, the more displacement it's causing within the fabric of space-time. And the more space-time is trying to collapse itself back in on itself. And the more other things it's attracting into it, right? So you can see then why, you know, the Earth has, you know, the mass that it has is disturbing space-time. And what's interesting too is that atoms are refreshing all the time. So let that sink in for a minute. I mean, you may have to go take a big bag of mushrooms to wrap your head around this one, but atoms are constantly refreshing at a rate of 10 to the 44th times per second, which means that the earth that you're standing on, the chair that you're sitting on, the sun that's spinning, all those atoms everywhere are being refreshed at the quantum level because they're all just energy potentials, right? So as you are moving through space, your atoms are being refreshed and rebuilt at the atomic level, at the quantum level. And they're becoming new atoms. They're changing as they're going through that, the Planck Length, you know, the space-time. And but there's already an energy pattern that's there. So when the atom gets refreshed, it's next to another atom that gets refreshed, which is next to another atom which gets refreshed, which is an iron molecule or something like that. So it maintains the integrity of that iron molecule as it's moving through. But then it comes up to the cellular level, then it comes up to the organic level, and it comes up to all those other sorts of levels. So you're three-dimensional with depth. and being refreshed as you're just walking around. Oxygen molecules that are flying by, the same thing's happening to them. You know, that's constantly happening at the tiny, tiny quantum scale. But it's the disturbance that each one of those atoms makes at the atomic level that puts that tension on the space-time, makes it want to collapse back in on itself. That's causing gravity. So, therefore, gravity proves that we live in a holographic universe. Anyway, food for thought. Love you much. Like, share, subscribe, blah, blah, blah. Share this around. Can somebody please send this to like a real physicist? Like, please send this to a physicist, okay? This is a concept that we need. We need this concept right now. In so many ways. You look at the things that are going on in politics, you look at the things that are going on in the world and in science, and you know, we're trying to get off the earth and we're trying to do all this other kind of stuff because we think that we're stuck in this universe of matter and material. We're totally not. We're totally not. You know, we are these individual points of consciousness. You can debate where consciousness comes from, but that's what we are. We're individual points of consciousness that are animated, you know, within this hologram of a universe, right? And with all the crazy things that are going on in the world right now, if we start to understand that and understand it responsibly, see, now I'll do another video later about like what the implications of this are, but share this around, you know, because this is an idea whose time has come. So if anybody out there, if you know Neil, if you know Brian, you know, any random dude at MIT or something like that who's like looking for the next big idea, please fucking forward this. Sorry. Please. Love ya. Bye.